Hello and welcome back to another IB Math Speedrun with me, Vince. In this one, we're going to be going through Chapter 9.2, which is about an introduction to vector algebra. So let's begin. So, what do we need to know? Actually, we touched on this a bit earlier, but we need to be able to express a vector in component form. So we can write a vector as equal to something times I, say xi plus yj, where I and j are, we call these unit vectors. So we have I, j, and k, and we call these the unit vectors. They represent one unit. Well, x represents one unit in the x direction. I represents one unit in the x direction, j represents one unit in the y direction, and in 3D space, k represents one unit in the z direction. So we can notate it as this. So for example, we could say 3i plus 2j plus 5k. Or we could also notate it in column vector form, which is when we write 3, 2, and 5. So a vector that has a starting point at the origin and an endpoint somewhere in any point in the plane, in space, is called a position vector of this point. So if this is the origin, then this vector is called the position vector. And so we write that this vector is equal to the origin to the position, which is equal to xi plus yj, or x and xy, where x and y, or this x is the horizontal component and y is the vertical component. And so now we can talk about some additions. So if we add two vectors together, this is simply equal to their components being added together. So we add the unit components, so a2j plus b2k, plus b2j, and we can also just add the column vectors. So this is a1 plus b1, and then a2 plus b2 over here. So yeah, that's that. And then next we have multiplication of a vector by a scalar. So if we are multiplying a vector by a scalar lambda, this is equal to lambda of a1 times I plus a2 times j, which is of course equal to lambda a1 I plus lambda a2 j. So we can distribute the scalar among the components. And if we are linearly combining two vectors, we have lambda a plus mu b is equal to lambda of a1 I plus a2 j plus mu of b1 I plus b2 j. So this is equal to the lambda a 1 I plus mu times b1 I plus lambda a2 plus mu b2 j. So that's how we linearly combine vectors, and in 3D space it's the same, we just expand for another plane. So given that, let's solve some questions. Sorry about that. So next, we need to do some questions. I'll do the odd ones. So we need to first, given the vectors a is equal to 2i minus 5j, and b is equal to negative 3i plus 4j, find the following vectors. First, a plus b, third 5a minus 6b, and next eth 3 over 5a plus 3 over 4b. So this a plus b is, we can add the components, so this is 2 minus 3, which is negative I, negative 5 plus 4 minus j. Okay, next we have 5a minus 6b, which is equal to 10i minus 25j plus 18i minus 24j. So this is equal to 28i minus 49j. Is that correct? Yep. And then this one, we have 3/5 a plus 3/4 b. So we have 6 over 5 I plus minus 3 j minus 9 over 4 I plus 3j. So those two cancel out. So this is going to be 6 over 5i minus 9/4 I, which is negative 21 over 20i. Yay! Okay, next question. We have the vectors p is equal to 3i plus 2j, and q is equal to I plus 5j. Express as a linear combination of vectors. So we have to do b 10i plus 9j, d I, and f negative 1/2 I plus 2/3 j. So how do we get 10i plus 9j? I think, is it just 10i plus 9j? Okay, so 10 is equal to lambda 3 lambda. Okay, because more or less 10i plus 9j is equal to lambda times 3i plus 2j plus mu times I plus 5j. So I can normally skip writing out this part, so we get 10 is equal to 3 lambda plus mu, and 9 is equal to 2 lambda plus 5 mu. So you can rewrite this as equal to 2 lambda plus 5 times 10 minus 3 lambda. So this is equal to 2 lambda plus 50 minus 15 lambda. So we have 50 minus 9, negative 41. It's equal to negative 13 lambda. Sorry, let's just say lambda. No. They've just expressed it in different notation. Oh, okay. They're not bad. So we have lambda is equal to 41 over 13, and so mu is equal to 10 is equal to 3 times lambda plus mu, so mu must be equal to 7 over 13. So then we can express this in the form 41 over 13 times p plus 7 over 13 times q. So yeah, it's cool. Next one, we need to express I. How we're going to do that is, well, we have 1 is equal to lambda 3 lambda plus mu, and then 0 is equal to 2 lambda plus 5 mu. So as usual, we substitute this as equal to 1 minus 3 lambda. So this is equal to 2 minus 15, so 13 lambda is equal to negative 5. Negative 13 lambda is equal to negative 5. So lambda is equal to 5 over 13. Mu being then negative 2 over 13. Since we can simply substitute lambda back into there. So this is equal to I is equal to 5 over 13p minus 2 over 13q. Okay, and then so for the final question, negative 1/2 I plus 2/3 j, we have negative 1/2 is equal to 3 lambda plus mu, and then we have not 2/3 j, okay, 2/3 j, so 2/3 is equal to a lambda plus, it's equal to 2 lambda plus 5 mu. So this is 2 lambda plus 5 times negative 1/2 minus 3 lambda. So this is equal to 2/3 plus 5/2 4, 15, 19 over 6 is equal to negative 13 lambda. So we have lambda is equal to negative 19 over 78, I think. And then mu is equal to 3, 18 over 78. Let's just, well, negative 1/2 is equal to 3 times negative 19 over 78 plus mu. So mu is equal to, this is, how do we express this in terms of over 78? 78 over 2, 35 plus 9, 39. 78. So this is 39 plus 3 times 19. So that's equal to, yeah, it's, sorry, 39, sorry, negative 39 plus 3 times 19, which is equal to 18 over 78, which of course equals, I think it's 3 over 13. So we have, whatever that was is equal to negative 19 over 78p plus 3 over 18q. Nice. Okay, on to the next question. A cuboid A, B, C, D, E, F, G, H with the vertices B is equal to 3, 2, 0, C is equal to 3, 2, 1, D is equal to 1, 1, 2, and G is equal to 0, 3, 1 is given. Find the coordinates of all remaining vertices. And so this looks like quite a tricky problem, but it's not. And what we get is, first let's label the cuboid actually. So we're given B, C, D, and G, so A, B, C, D. So I guess I want to have C here, B here, D here, and G here. So this is A, B, C, D, E, F, G, H. And so we actually can find this using unit vectors. So if this is 3, 2, 1, this is 0, 3, 1, this is 3, 2, 0, and this is 1, 1, oh, not that one, this is 1, 1, 2. And we know that these are all tangents. So more or less, CG is equal to BF. So if we take the difference, or actually, as you can notice, the difference between B and C is just 1 in the Z value. So the difference between G and F should just be F is 0, 3, 0, since we just subtract 1 from the Z value. 1, 1, 2, so we have to get from 3, 2, 1 to 1, 1, 2. So that's a vector of negative 2, negative 1, 1. So if we add this to G, we get negative 2, so 2, 2. E will then be 0, 3, 0 plus this, so this would be negative 2, or I can just subtract 1 from this, really. So negative 2, 2, 1. And finally, A will be equal to 3 minus 2, 1, 1, 1, 1. So these are the coordinates of all of the quarters. We can just use vectors to solve it. Nice. Okay, and so do we have to prove the commutative? Okay, fine. We have to prove associative and opposite. So we have to prove for vectors that A plus B plus C is equal to A plus B plus C. So I guess we need to label C as a vector in some form. C is equal to Li plus Pj And so for all A, B, C, A plus B plus C will be equal to, actually no, let's label all of the vectors. So we have A is equal to Mi plus Nj, B is equal to Xi plus Yj, and C is equal to Li plus Pj. So what we have over here is Mi plus Nj plus Xi plus Yj, all in brackets, plus Li plus Pj. And this is equal to Mi plus Nj plus Xi plus Yj plus Li plus Pj. And so all of this is equal to, for both sides, this will be equal to Mi, M plus X plus L times I plus X plus Y plus P times J. And so it doesn't matter, since these are all real numbers, it doesn't matter which way you add the brackets. So this proves the associative property of vectors. Next, for opposite elements. So for all vector A, there's an opposite element, negative A, such that A plus minus A is equal to negative A plus A is equal to 0. And so we simply let A is equal to Xi plus Yj. So negative A is equal to negative Xi plus minus Yj. So A plus negative I is Xi plus Yj minus Xi minus Yj. So this is equal to X minus X plus Y minus Y, I times J, which is of course equal to 0. So that is our answer. Yep, so that proves that property. So finally, we have the last question. Use the properties of real numbers to show the following properties of multiplication of a vector by a scalar. So the first property is that lambda A plus B is equal to lambda A plus lambda B, which of course this is equal to, A is equal to Xi plus Yj, B is equal to Mi plus Nj. So we have lambda of Xi plus Yj plus Mi plus Nj is equal to lambda Xi plus lambda Yj plus lambda plus lambda Nj, which of course it does, because we can just expand this just the same as real numbers, so they equal. And then finally, we need to prove that 1 times A is equal to A. So A is equal to Xi plus Yj. So this is 1 times X plus I plus Yj. I mean, 1 times each individual component, probably, is equal to X of I plus Y of j. So 1 times X of I is simply X of I plus 1 times Y of j is Y of j is equal to that. So that was all. That's proven. So that was all for the speedrun. I hope you enjoyed, and I hope to see you in the next one. See you then.